All right, hello everyone. Welcome to recitation 3 for this class. Today, the topics we'll be covering is the use of deep learning in reinforcement learning, neural network architectures, and then we'll have some time for questions about the material we've recently covered, which is Monte Carlo learning and temporal difference learning. And then if there are any remaining questions for homework 1, we'll be having time to go over those as well. Okay, so first, why do we need neural networks in deep learning? If you've started homework 1, you know that we do not use any neural networks in this homework. We simply have a sort of queue table containing states and actions. But if we have too many states and too many actions, or like continuous states and actions, we cannot think of something like an Atari game, Brick Breaker. An image from one of those games could have so many different states depending on the different arrangements of pixels. So it's no longer efficient to use a Q table in order to make estimates of a value. We do need function approximators, and that's why we need deep learning. So for the rest of this recitation, we'll be going over some common neural network architectures that you'll see in a lot of the papers we read. So the first is just a multi-layer perceptron. Very simple. So a single perceptron is one of the most simple machine learning algorithms, and it can only separate linearly separable data. But once we use multiple of these, put in layers, and use nonlinear activation functions, and NLP can separate non-linearly separable data as well. They're fully connected, which means in each layer, every node has a connection to the ones in the prior layer. So, for example, if we have 3 inputs and 3 hidden units in the hidden layer, there would be 9 different weights, as 3 times 3 is 9. And between each layer, we also have an activation function, which introduces the nonlinearity, which could be a tanh, Raven, or a softmax. Then we move on to convolutional neural nets and convolutional layers. So in in reinforcement learning, we'll often work with image data. So again, this could be inputs from Atari games like Brick Breaker or Tetris, and then also could have like image data from self-driving cars. And then we really need convolutional layers before we actually do the value estimation part. And the reason we need that is to reduce dimensionality and extract certain features that may be useful. And does anyone not know what like a convolution operation is? Okay, that's good. Then I'll just summarize it anyways. It's just you have a filter or a kernel that slides across the input, and you basically take a dot product of the filter and the part of the input that you're on, and the output of that is a feature map. Yeah. So what are some benefits to using CNNs? Well, they're slightly different from MLPs in the sense that they're more biologically inspired, especially by the human retina. And instead of looking at the input as like one whole thing, we kind of break it up into subsections. And this reduces the number of necessary parameters as we can use weight sharing and sparse connections. So what are those two things? Well, the kernel has fixed weights that don't change when sliding across the image. So those parameters are shared. And then sparse connections, unlike MLPs, which are fully connected, CNNs are not, which means that there's fewer weights to keep track of and fewer parameters. It takes advantage of the fact that pixels that are close by to each other are more strongly correlated than those that are farther away. So as you can see in that image below, instead of looking at the face as one whole thing, we can kind of break it up into different features and use that to analyze the image as a whole. So in these layers, typically the the earlier on the layers are, they extract lower level features, and the later layers extract more complex features. But also keep in mind that the features that they extract may not be something that humans understand. It is just a latent representation that the network can use. So it's not like later layers will output like eyes and nose and mouth for a face. It's just a representation that the network understands. And this is a summary of how to actually compute what the feature map or the output layer from a convolutional operation would be. So if we were to have an input layer containing a specific width, height, and depth, and we have a convolutional layer with k filters. Spatial extent would be just its dimensions, so width by height, and a stride, so how many sort of units to skip when like sliding across that layer, and zero padding. So the output layer would be given by the following formulas. So we have width 2, height 2, and depth 2. Yeah, is anyone confused by any of the calculations in this picture? Yeah, so if we look at a network that uses convolutional layers, we can look at AlexNet. This is one of the best image recognition networks at the time. And so using the formulas in the previous slide, we can see that if the input layer was 227 by 227 by 3, then if we were to use a convolutional layer with an extent of 11 by 11 and 96 different, and like k is equal to 96, so that's 96 different layers, then the output would be 55 by 55 by 96. And through this operation, we've reduced the number of parameters from 150,000 to 35,000. And you're probably wondering what the 96 layers would be for. Well, those are just different types of convolution. So if you look at the image down below, different kernels can give us different outputs that may be very useful to the network. So, for example, you have the Gaussian blur, you have sharpen, you have edge detection, and those different layers, when put together, can tell you a lot more about an image than its raw input. And after every convolutional layer, you typically have a pooling layer. And what they do is they further reduce the dimensionality of the feature map. And they basically highlight or summarize features in the feature map, which can be helpful when there's similar images, but they're slightly different in terms of rotation or position. And that makes them far more robust to like these small differences. The most commonly used ones are max pooling and average pooling. So in the image below, you can see what max pooling looks like. So if you have a filter of size 2 by 2 with a stride of 2, 2, 2, then we basically are looking at what the largest value is in each of these 2 by 2 squares. Does this make sense? And then we can look at how this is used in deep reinforcement learning. So this is the Atari with DQN network. So it learns different types of Atari games and how to beat them. And as you can see, before we get to the dense layers and before we actually output an action, there's a lot of different convolutional layers that reduce the input from 84 by 84 by 4 to all the way down to just 64 3 by 3 filters. So yeah, that greatly reduces the dimensionality, and then we need fewer hidden layers for the actual like Q-value computation. Next network, we're going to look at our recurrent neural networks, or RNNs. Unlike CNNs, they're used for sequential modeling rather than just spatial modeling. And they can handle variable number of steps, and they don't need a input of a fixed length, which makes them more versatile to different types of inputs and outputs, which you can see below. A one-to-one would be the same as an RRN, a CNN, but the rest of the inputs you can see in what cases they could be used as. So we could feed in one image and get multiple outputs. That could be like a use case in image captioning. If you were to feed in a vector of words like "this food is bad," you could get a sentiment analysis. So that could be either like good review or bad review. You can have machine translation, in which you again input a vector of words and then output a vector of words. And you can also have many-to-many, which is something like sequence tagging. So yeah, those are different use cases of RNNs. So here's a little bit of how the actual inputs and the weights are actually calculated at each layer. So as I mentioned before, the sequence of an input is important for our RNNs because, if you can see before, each hidden layer takes in not only the input from the current time step, but it also cares about what the output of the previous hidden layer was. So that's why order is important. And now if we look at this, if we have an input from like an input X that goes from 1 to a time step T, each hidden layer would have an activation function, and the value that feeds into the activation function would be the weight matrix times the output of the previous layer, plus a different weight matrix multiplied by the input at the time step T. So keep in mind, this W, like WHH and WHX, are a different set of weights. And then the output at every time would be some sort of activation function, in this case softmax, but that can be different. And what's in that is a third weight matrix multiplied by the output of the hidden layer at that time step. So the main things to know from this is that the weights used for input, hidden state, and output are all different, but they're the same at every time step, and they're only updated at the end through backpropagation. Okay, so I'm sure everyone knows how backpropagation works. So once we get to the output, we have we compare our output by the actual value, and that gives us a loss or an error, and that error is like backpropagated to update weights in previous layers. So this leads to talking about the vanishing or exploding gradient problem. Basically, our error, our partial derivative of the error with respect to the weights, would be the sum of these errors from time step 1 to the end. And each of those, that partial derivative is the sum from 1 to the current time step that you're on of the partial derivative of the error respect to the output respect to the hidden layer at that time step, and then the hidden layer at that time step with respect to all the previous hidden layers before it, and then the hidden layer before with respect to the weights. So the main term that we want to look at is the one highlighted in red, the partial derivative of the hidden layer at the current time step that we're on with respect to all the previous time steps. So this part of the math is not super important to like fully know what's going on, but the main takeaway from this is that if we have an activation function like tan H or softmax, which outputs values between 0 and 1, and we have multiple hidden layers that come before that. If we keep multiplying by such a small value, eventually the gradient would be very, very small as well, which means that when we update our weights, they're not going to be changing by a lot. So the weights are basically stuck in a certain position and you're not really learning anything. And that's what's called the vanishing gradient problem. And the opposite of that is the exploding gradient problem. You're multiplying by a very high value so many times. And that basically causes the same issue as well. Okay, so how is that solved in, oh wait, sorry, any questions about the math over here? So the diag is a diagonal matrix that represents the partial derivative of the hidden states, and f prime is an activation function. It could be softmax or tanh. Questions about that? So what are some possible solutions to that in our RNNs? One thing we can use is gradient clipping. So this solves the exploding gradient issue as it prevents gradients from exceeding a certain threshold. You can truncate back propagation. So instead of multiplying by those small values for each and every hidden layer that comes before that, we only do it for some of them. But then, of course, the issue with that is that a lot of the previous parameters do not get updated or get updated incorrectly, which is not what we want. We can make some tricks to weight initialization. So instead of having the weights in between 0 and 1, we can have them start at something slightly higher. And yeah, that makes the multiplications not drastically reduce the size of the gradient. And typically with the weight initialization trick, some of the activation functions are switched to ReLUs. So you're not bounding the outputs by 0 and 1. And then the last solution is to use different architectures, and to add different components to the RNN, which we will be talking about next.
Okay, so I'll talk about another issue of RNNs first, the long-term dependency problem. So this is essentially when the recent information is not sufficient to capture whatever you want to predict. So if you consider the following sentence, I grew up in Brazil, the largest country in South America, and I speak fluent blank. In this case, the recent information like speak and fluent give you some indicator of what the most likely next word is, which would be like some sort of language. But you can't fully get that information without looking at the country Brazil, which implies that it would be Portuguese. So to resolve this problem, there was a network architecture called the LSTM, which stands for Long Short-Term Memory. It was invented in 1997. And it's a type of RNN that uses a lot more complexity within the hidden state to capture much more complicated relationships. So yeah, here's a little bit of notation for the diagram. These yellow boxes refer to like a single neural network layer followed by whatever the activation function is. And these red circles represent element-wise operations. So like the multiplication you see here is not a matrix multiplication. It's a multiplication where each element is the product of the corresponding elements in the two input matrices. So one of the key innovations of the LSTM is the fact that it uses a cell state in addition to the hidden state. And the cell serves as an information pathway that crosses the entire chain. And how it's unique is that it only uses element-wise operations. And this allows you to flow information without making drastic changes. Whereas in an RNN, you multiply by weight matrices and activate and apply activation functions, which causes your hidden state to vary drastically across time. But in this case, it flows without major modifications. So one of the fundamental units of LSTMs are gates. And essentially how that works is you have a sigmoid neural network layer over here, followed by an element-wise multiplication. So your sigmoid layer gets you values between 0 and 1. And when you do an element-wise multiplication, you essentially either forget the value if your sigmoid gives you 0, or you retain the value if you have like a sigmoid value of 1. So this is essentially a way to get optional information flow. So you can either keep the memory that already exists, or you can erase it. Does this make sense? Okay, so there's 3 gates in an LSTM. The first gate is called the forget gate. It takes in the concatenation of your hidden state and your input state, and you apply the sigmoid layer, and that gets you a matrix that represents how much of the original cell state you want remembered. Then you have an input gate. It consists of 2 components. First, you have a cell update, which is where you take your hidden state and input state, and you apply the weight matrix and tan-H activation function. And this represents how much you want to change the original cell. And your input gate is similar to the forget gate, except it tells you how much of the cell update you want to use, like what parts of the cell update should be reflected within the cell.
So this is how the cell state update works. You first multiply the forget gate with your previous cell state, and then multiply your input gate with the cell state update. Does this make sense to everyone? Okay. So finally, you have an output gate, and this essentially tells you what you want to return from the cell state and output it through your hidden state. So how this is computed is you compute the output gate the same way you computed the other gates by applying a sigmoid activation function over a single layer with your hidden state and input state, and then you then do like an element-wise tan-H on your cell state, and then multiply the output gate by this tan-H applied to the cell state, and this essentially gives you it essentially returns a part of your cell state through your H sub t. So to summarize, this is kind of the overall architecture. You have the forget gate, which determines whether or not you keep part of the old cell. The input gate, which tells you what part of the cell update you want to write to the cell. And then the output gate, which tells you what to read from the cell and add to the H sub t, which is the output. And this kind of precise control flow is what allows LSTMs to be so powerful. One important feature of LSTMs is the fact that backpropagation works a lot nicer than it does in RNNs, and it avoids this exploding and vanishing gradient problem that you saw earlier. And the reason it does that is because the only 2 operations that happen to the cell state over time are element-wise multiplications and additions, and these 2 operations inherently don't produce like very large or very small gradients, whereas like multiplying by weight matrices and applying like activation functions continuously compounds the gradients up or down. Yeah, so there are a couple of minor variations to LSTM that people use. One thing you can do is add people connections. So this is essentially where you have the forget gate, input gate, and output gate also take in this previous cell state as input. And this is just a minor change, and different papers can use different variations. They might not include the people connection on all of the gates. And in some cases, it's shown to improve performance. Second idea that people have had is coupling the forget and input gates.
So this essentially means that we first treat the forget gate like we used to before, but rather than calculating the input gate separately, all we do is 1 minus the forget gate. So essentially what this means is that we either keep the old value or we replace it with the new value in the update. Rather than having like being able to keep both the old cell value and the update, we kind of like balance by weighting the two. So now I'll talk about some of the flaws of LSTMs. The first is that they're still highly sequential. So there's no way to parallelize over within the sequence itself, and that leads to slow computation. The second issue is that you have this bottleneck where you have the cell and hidden state, which captures all of your information that goes across elements of your sequence. So if you, for instance, taken an entire sentence and then need to produce a translation, by the end of the sentence, you kind of need to capture all of the information in that sentence, and that can be very difficult. And then the final issue is that of unidirectionality. So the LSTMs we saw currently were unidirectional, but there are variants that go in both directions. But in either case, you're unable to capture relationships between elements that are far away, which is probably important if you're doing like some sort of sequence modeling. Okay, does anybody have any questions about LSTMs? Okay, if not, I'll introduce transformers. They're essentially an architecture that seeks to resolve some of those difficulties I mentioned on the previous slide. So the core of transformers is a concept called attention, which essentially means that we have some way of choosing which features we want to pay attention to or give emphasis to. So we weight relative importance of different parts of the sequence. So for instance, in the top picture, you can see that there are certain matching between, like, say, European and then the French word for European. And also you can note that, for instance, the word the, or the word la, which is the in French, is mapped to by both the word the and the word area, because la takes into account the noun as well, because it's feminine, right? And this sort of shows kind of the complexity of the relationships that you can capture this way. And then it's obviously also applicable in vision, because you kind of also want to pay attention to different components of images, for instance, as well as sentences. So the benefit kind of attention is that you have a mapping from every input element of your sequence to every output element of your sequence. So you can essentially solve that long-term dependency problem that I described earlier. And there's also no bottleneck anymore because information flows all the way through. There isn't this sort of context vector that has to hold all of the information about a particular sequence. So now I'll talk about the specific mathematics behind attention. One commonly used variant is dot product attention. So you take a query and a set of key value pairs, which are all vectors, and then you find the dot product of each query with the key, or the query with each key, and then apply a softmax function on that, and that gives you the weights that you should apply for each of the values. Yeah, go ahead.
Is the softmax like a fundamental part of the attention mechanism, or is it just something we do to normalize and we can use other things for it?
Yeah, so the idea is that you want to weighted sum of the v sub i's. So like the easiest way to get like all the weights to become positive and sum up to 1 is just by using the softmax, right? E
gets you to positive, and then you divide by the sum for normalization. There's obviously alternative methods you can use, and you don't necessarily need to use dot product for similarity as well. Okay. Now I'll talk about how you kind of just transform this to write this in matrix form. In this case, essentially, you just have multiple queries as well as multiple keys. So you just can vectorize this whole quantity by making it the row-wise softmax of Q times K transpose, and then multiply that by P. And this allows more computations to occur in parallel. And there's one minor issue with dot product attention, and that's that as dk grows large, the variance of qt, q transpose times k gets large. In fact, it scales by square root of n. And this means that the values in the softmax get very large, and then your softmax gets a peak. So most of the values in your weights will be 0, and then one weight will be 1. And this kind of causes your gradient to be small. And the simple solution that the people who invented transformers found is that you could just divide by the square root of dk, and that essentially normalizes everything and prevents these gradient issues. Does this make sense? Okay. Now, one interesting idea that is that you can use attention where your queries, keys, and values all come from the same place. It might sound like a little bit strange, but the idea is that you can look at it as like a soft dictionary lookup, where each of the keys are your individual elements in your sequence. Your query is one of those elements in the sequence, and essentially that dot product measures the similarity between the key and each of the queries, or the query and each of the keys. So, for instance, if your query token is bank, you look at the similarity between bank, that would be very high. The similarity between river would also actually be very high because river kind of disambiguates the meaning of bank from a monetary institution to a river bank. And while the other words kind of have low weights because they don't have that much of a relationship. So this essentially in some sense combines the meaning of the word bank and river, and so it provides a lot more information. Does that make sense? Any questions? Okay. So then one way we can make dot product attention more sophisticated is by providing multiple ways for the query key and value to be chosen. And how you do that is you just create H different layers, and you map Q, K, and D to each of those spaces, and using weight matrices, and then apply attention separately on each of those H layers. And at the end, you can concatenate them all and apply a linear layer. So now I'll talk about how that kind of fits into the transformer model. So the transformer is primarily composed of this transformer block, and each block has kind of two main components. It first has a multi-head attention, which I just described, and then it has a feed-forward neural network. Specifically, in the case of transformers, it's a two-layered neural network with a ReLU activation function. And the interesting thing to note is that they have two additional kind of features that makes transformers easier to train, and that's the residual and the layer norm. So residual connection essentially takes your value from before the multi-head attention or before the feed-forward network and adds it to the output of your multi-head attention. And what that essentially does is it shortens the number of steps in the gradient backpropagation. So it allows it to train faster rather than having like a very, very long difference between like the first layer and the last layer. There's kind of these shortcuts which help train. And then the second optimization is layer norm, which essentially changes your inputs to have mean 0 and variance 1 for each layer and for each training point, which also helps with training stability. So finally, this is like the entire architecture for the transformer. So we essentially have n of these blocks for your encoder. In the original paper, they had 6 blocks, but you can have a huge number, and like for something like GPT-3 or any of the recent like transformer models, you'll see like billions or trillions of parameters. And here for the decoder, there's a slight modification to this structure. Firstly, they used masked multi-head attention, and what this means is that you, rather than taking in all of the elements of your sequence for your attention, you only take in the first like k of them, because you don't want to give your model future information, and in this case it like hides that information. The second thing that's different is that you have this multi-head attention where you have inputs from both your encoding side and your decoding side. So this is called cross attention, and it essentially allows you to relate the input and output sequences together, which would be very useful. So finally, I'd like to show a visualization of the transformer that kind of shows that each of these heads produces something useful and distinct, and each like contributes like some structural understanding of the sentence. And you could imagine that after like combining multiple of these and applying the same transformation multiple times, you could learn something very significant. So that's it. Do you have any questions about transformers or about homework 1 or anything else?
That's all we have for recitation 3. We'll be standing here for a bit if anyone has any questions.